Welcome to this short video on sample preparation. My name is Jim Colvin. I'm the CEO of FA Instruments. I graduated Purdue. I have 38 years of contributions to the failure analysis community through various organizations such as ISTFA, EOS, ESD, IPFA, and IRPS. I have 15 patents that relate to the semiconductor field. I'm currently serving on the EDFIS Board of Directors, and my two most recent publications are in the Microelectronics Desk Reference. This is the outline of what I'm going to be covering today. I'm not going to go through all these in detail because these will be covered in their respective sections. If you wish, you can pause here to read these items. So the first thing we're going to cover are machine requirements. So we're going to overview the modules and the mounting methods. The first thing I want to talk about on the machine is how to fit large boards on. So there's an open design where you can place a rather large motherboard in the machine, and you just need to be aware of this Ymax value. This is 7.5 inches to the back mast of the machine. The device can be processed from beginning to end. So you can have it on the board, you can do the thinning, you can do the inspection, you can do the polishing, all of that including the RST measurements without removing it. This allows us to get the submicron precision out of the machine. The endpoints can be based on time, position, force, or capacitance and resistance functions, which we'll be going over in the next few slides. Some other features: image overlays, curvature compensation, adaptive mesh mapping, and in situ remaining silicon thickness. So as I mentioned earlier, by being able to leave the part on the machine, we can do the RST measurements. So by combining mapping and polishing, this is what makes the high resolution control possible. So you start out with a curvature mapping model. So this is an R-squared model where you're actually defining a curve and forcing that curve on the part. This is based on thinning the part, measuring the RST thickness variations from center to edge, and then matching a curve based on the tip diameter. Once that curve's established or surface is established, then you add in the mesh map, and after you've added in the mesh map taken from the interferometer and you define that surface, then you use something called surf. So what surf is doing, it's a surfacing control. It takes out the error in the force sensor so that you have a very deterministic Z head as the part is contouring the surface. So by combining these functions, we can get submicron accuracy out of the machine. There's also image overlays. This is if you want to target a particular area. You can load in diagrams, x-rays, or even image of the same part or similar part that's been prepped previously to use as an overlay. So the endpoint I alluded to earlier, the way this works is you have the tip biased with a 3.3 volt high impedance pulse, and then you have the lower plate which is tied to a high impedance amplifier. So we're sensing the pulse through conductive or semiconductive water. Because the water is contaminated when you're thinning, it's automatically going to be slightly conductive. So as that water plate approaches the die, the capacitance increases, and then once it reaches any one of the bonds, which you can see over here on the right side, once it hits these bonds in this area, then you're going to get an endpoint response. So you can set the machine to trip based on that endpoint response to make the process somewhat automatic. So let's talk about mount considerations. It's very important to make sure that the sample's properly mounted. So when you place a sample on here, you want to be sure that it's secure. It could be nylon screws, it could be a hot melt wax, and you also want the part to be aligned so it's squared up to the machine. So in these examples, you can see in the plate on the left side, the part is actually sitting inside of the edge of the milled aluminum. And there are relief corners in these areas here on the four corners. So this part is just centered on this corner, and then the screws are put in to hold the part in place. The reason we use the nylon screws is because they will actually bend and flex so that you don't crush the balls on the part. In the middle section, same thing. I have the part fit into the area, which is milled to be the same size as the part. And the plate on the right, this one I have two different part sizes that are shallow pocket that I can use hot melt wax to hold the part in place. What about boards? So if you have very large motherboards, this board is so large, but the part that we're going to be thinning is offset from the center. So it still meets the tolerance from the DUT stage to the back mast of the machine. On the right side, we have some very tall RJ45 and USB connectors, which would actually strike in the back of the machine. So by having this face forward, we mitigate that problem. With 2.5 3D die, you have to be concerned with, when you have multiple chips, are they all the same thickness? And they typically do vary by 5 to 10 micrometers in thickness. So be aware of that when you're thinning, as to which one is your target die and whether it will be thinner or thicker than the die you're not interested in. What about underfill? In this case, the customer wanted me to thin this die, but there was no underfill. So I added underfill using the little internal thermoelectric plate that's on the machine, so I could actually observe the underfill creep underneath the die. So I used an EP3UF underfill, and this underfill cured in about 20 to 30 minutes. So one of the hazards you can get into is assuming that you can pry the lid off the part. So in this case, the aluminum was, or the copper was milled along these edges here. So the copper was milled out, a slot mill, and then the lid was pried upwards and out, and the lid just didn't want to budge, and then of course using too much force it popped. And this area here, this is remnants of the silicon that ripped loose, and this is where it ripped. This is the area it ripped loose over here. So be aware of the construction of materials and whether or not you can pry it, or must you mill the lid. And in this case, you must mill the lid completely down to a foil and get into the eutectic die attach and then remove it. So let's talk about tip convolution simulation and tip diameter selection. So with tip convolution, the diameter of your tip versus the surface it's going to run on, the bigger the diameter of the tip, the more trouble it's going to have covering the surface properly, even if you're writing on this edge of the tip. And so in the illustration here, what you actually want is you want the tip edges to be calculated with the convolution, so that edge of the tip will follow. So it'll follow through this path here. And this way you can get the submicron accuracy because you're using the mesh models in conjunction with the tip. So in looking at a simulated model, in this case, this part has a very high curvature warp. So this one was thinned down. So 650 microns of silicon was removed. It started at about 750. So that left 100 or so microns remaining in the center. And you can see the edges are much, much thicker, about 150. So we got about a 50 micron variation from center to edge across maybe 8 millimeter or so distance from center to corner. So if I use a 3 millimeter tool and I calculate it, I adjust the X curve and Y curve sliders to model this R-squared curvature to try to flatten it out. So we flatten the curve. You can see this area is going a little bit negative, and these areas are all a little bit lower than the rest, and that's because the tip diameter is too big versus the curvature of the part. So you can, by doing this, you can simulate, play with different tool diameters, and predict what your results are going to be before you remove any silicon. Now, how about the change in curvature of the part? As you're thinning these down, what happens is, while you're removing layers of silicon, the work curvature is actually changing. So this is a dynamic event. And so the best way to approach these is to go ahead and do what I call flat topping the part, where you remove the silicon and you don't worry about the curve, you just flat top it. Take it down to about 100 like that previous curve showed, or even 50 if you're going to say 20 or 30 microns or less. So you thin it down, and that gets rid of most of this relaxation. And then from that point forward, you're just going to do the curve plus mesh models and let the machine iteratively correct the smaller changes in the curvature of the part. So they're at minus 20, 27, then they're minus 23, and then they're minus 20. And so even with the 5 millimeter here, the curvature is light enough that we can get away with using this large diameter tool and not get into convolution issues. Once that's established and you have removed a small amount of silicon to create that curved surface, then you measure that surface, you transmit that mesh model into the machine, and now you're taking the curve you've already created and you're adding this RST mesh model. And with these two running together, you're now greatly reducing the errors in the surface based on what the irregularities of the part had versus the theoretical curve that you're trying to use. So let's talk about thermal and measured curvature strain. So this part has a low crack risk because you can see at ambient temperature, we're running in the minus 27s, and on this machine, if you're seeing minus 45s, that's where you really need to be thinking about thermal. For anything, minus 30s, minus 20s, minus 10s, those are fine. Now, if we heat this part up just to show how much it relaxes, you can see we're in the minus 27s, and we can see that the edges are about 35 microns deeper than the center. If we heat the same part and do another drop-down profile measurement on the machine, we find that those edges are now about 12 deeper than the center. So it's changed quite a bit from what it was previously. And you see the X and Y curves are now minus 7s, minus 9s, so much less curvature. Now remember that chart you saw earlier where as you thin it, the part relaxes and changes. So what will happen is as you're heating and thinning this part down, once you get below, say, 100, the curvature is going to relax typically on the part enough that you no longer need thermal. So typically you want to do the thermal, thin the bulk of the material off, turn the thermal off, remove a small amount more material with an extra fine diamond tool, then do your RST mapping and go from there. So what about a large board? This is a Peltier that's placed underneath the board with a thermal pad material, and then on the image on the right, this is an IR image of the actual heated part to 80 degrees C to see that we're getting the uniform temperature we want on the part for the thermal relax. And again, once this part has been globally thinned and we're below 100, we can turn the heat off and then proceed normally from there. Well, what about thermal management when it has to do with the part itself dissipating power? Well, in that case, what you want to try to do is limit your viewable area where you must thin and leave the silicon thick in the other areas where you've got a great deal of heat generation. Because remember, once you thin the part, you no longer have any lateral ability to dispense the heat. And so if we look at a local polishing technique versus this trenching technique, you can see this area is red to white, which is hotter, and it's a little bit cooler here. And so what you're trying to do is set this up where only the trench area is where you're going to actually be taking your measurements, and you're leaving the silicon thicker in the other areas to do a better job of heat dissipation. So with power devices, this is something you've got to keep in mind. Now, what about the properties of silicon in terms of its translucency, and how does it respond when you go ultra thin? In this case, we have the Lambert-Beer absorption law, where with a light of intensity I0 is incident on a piece of bulk silicon, the light's attenuated based on that thickness of silicon as a function of its wavelength and its doping concentration. So if we take a look at the next slide, so this is how that affects this for a lightly to undoped piece of silicon. So you can see the 1064 gets through fairly well, 1064 nanometers. But as we head to the red wavelengths, the 671, you can see that we're now below 10 microns to even get through. And so we really want to be, about 5 microns, 3 microns kind of stuff. And that's the interest in being able to do the visible SIL lenses, to get into the visible domain so that we can resolve smaller devices. Now, what does doping do to this? So if we look at the dopant concentration, you can see that your transmission falls off even at the band cap. You can see that we're looking at about maybe 8%, with the heavily doped silicon, versus a lightly doped, which is going to be around 60% or so. And then as you go to longer wavelengths of IR, you can see the dopant attenuates even more heavily the image that you're going to get. So this is a challenge for the interferometer if you're looking through thick silicon, because the dopant concentrations are going to limit what you can pick up with the interferometer. So you'll have to thin some and then measure. So with ultra-thin silicon, well, what are the issues? Well, when you go really, really thin, it's not a matter of whether the machine will do it. It's a matter of whether the part can withstand it. So the quality of your underfill, the type of strains you're dealing with on the part, all factor into this. And so if you look at this part, this one's been thinned down, ultra thin, and you can see that on this side you see these are where all of the bumps are, and they're putting strain on the silicon. So the silicon acts like saran wrap, and you can see in a laser interference mapping, you can see where all the bumps are, the irregularities of the fringe patterns, the moire patterns around each of these bumps. And so if you heat the part up, you'll see the bumps appear. If you take the part to the temperature at which you prepped it, you'll see the bumps disappear. And of course, obviously, you wouldn't want to reflow a part when it's this thin. It's unlikely that it would survive. So what about dissimilar materials and polish contamination? So when we're prepping a sample, these are a few examples of how to understand a surface. So here's flat and smooth. Here's flat but rough. Then you can have smooth but not flat, or it's not flat and it's rough. Typically what you're going to be seeing is the top surfaces. So you're going to have flat and smooth, or you're going to have flat and rough until you get to flat and smooth. If you over polish the part, you will end up with the third circumstance, which is smooth but not flat. So with pits or defects on the part, you can get multiple peaks coming off the interferometer. So be aware of that. When you're doing measurements, you'll occasionally get outlier data points. So how do we know when we're done? Well, on the machine, looking at the part on the left, you can see there's still some tool marks on here. Now this is with the diamond paste, but if I go to the NIR, I don't see those tool marks. So if my goal is to do infrared photon emission, this is good enough. But if I want to go further for, say, FIB or SIL lens technologies, then I would go ahead and do the colloidal polish as well. In the process to shorten the cycle, so these are the tool marks from the diamond. Then switching to a diamond mylar tool, you can see that this is a much better surface. It's more of a matte finish, and the tool marks are now gone on the part. So by doing this intermediate step, you can go straight to the colloidal silica step. So this shortens or bypasses some of the diamond steps. So now let's talk about forming the surface. Once we've thinned the worst of the silicon off, we turn the curve on based on those set curve parameters. We run a spiral pattern, and we define this surface. And so once this surface is close to defined, we turn this surf function on. So this function here we turn on. And then the part, once the forces settle out with the force map, which I'll show in a subsequent slide, then we're ready to go ahead and measure the surface. We take an RST map of that surface, we feed it into the machine, and then we switch over to the diamond paste with the Xylem tool. Well, you can see in this image that there's some contamination that generated some streaks at this point based on the angle of the tool. And so what had happened was some of the glass particles were picked up out of this underfill, and they got caught in the tip, and so as the tip got to this particular angle, it started to generate these streaks. So what this means is we need to clean up or redress the tip. So you redress it with a razor blade, you do it on end to dig a little cup in the bottom, and then you just flat mill it or flat grind it with the razor blade with the spindle running. Then you're ready to proceed with the same tip. Second option is throw the tip away and put another tip in. So now, same part. Now you can see we've gotten rid of those artifacts and we've got a uniform matte finish after the yellow paste. Now you can notice these little terrace marks. Looks like an X or an hourglass running along here. And that's perfectly normal. That's a very subtle optical effect. As we go into the polishing steps, that'll completely disappear. You won't be able to see it. Once you enter these polishing steps, that's where you get rid of those subtleties on the device. So this is a soft polish using a cotton bud, and this is using the green paste, which is an even finer diamond grade paste for achieving the polish on the part. So now that we've done that, the large area, we want to thin a smaller region of that large area below 5 microns with about half a micron variance or better. So we're going to use the adaptive current algorithms to do this. So the first thing we do is we correct over this particular area that we're going to do the thinning. We treat this as a new part. We do the automated drop down tilt measurements. We define, with this area defined, we go ahead and grind a little bit of material off. And then we proceed the same way as we did before, where we're adding the mesh maps and the curves into this. And then once we've done that, we switch over to the diamond paste, and we use this feed mechanism where we're slowly feeding the tool, because the tool is wearing. So the paste is wearing the part, but it's also wearing the tool. So by using a slow feed, we compensate for the wear of the tool with the surf turned on, the mesh turned on, and the curve turned on. And the only thing we don't know is how much material we've removed. We have to judge that by time. But we do know that we're generating a flat surface. And how we know this is based on the force map. So the force map on the left shows there's still high spots, especially around the periphery. As we let the process continue to run, the map on the right settles out. We've just got a little bit of a very edge frame. So this is now a good time to stop and then do another RST map. And we load the new RST map into the current map, and it puts a little more down pressure on these areas that weren't cleaning up. So it's adaptive, as I've mentioned. Now in this area, you can see there's some rough pitting in this region. In this area here is the rough pitting. What this tells us is that we stopped too soon. So resume with the yellow polish, run another set. Once this is all uniform, then you know that you can proceed to the next finer polishing step from where this one is. Then we go to the colloidal polish. So this is a colloidal silica that's being polished. You can't see through it with visible light. If you go to infrared, you can actually see the circuitry. So see the circuitry glowing from underneath in a few areas here as this is thinning. And this can be useful because as the colloidal silica starts to get filled with regular silicon particles, this will become less transparent in the near IR. So you know that your colloidal is starting to get too contaminated, and it's a good place to stop. I typically just use the 15-minute rule when I do this. So now we're at 6 microns, and you can see right here, you see there's a little bit of a scratch or a score right here. And so we'll go a little bit longer. And now we're at 4.76 microns, and you can see that scored area is now gone. And our goal is to reach about 3 to 3.5. So we just continue polishing with the colloidal, and now we're at the 3.5. So you can see in this mesh model, 2.8. And then these edges out here, this is where the area lips up, and it can't read on the visible interferometer. So we're limited to about 9 or 10 microns maximum for the visible interferometer. You can roll this on its side and get a cross-sectional view of how the floor of your part looks. And then this is the exact same data represented in a contour mesh. These white areas in the corner are because the visible interferometer could not read these thick areas here. So the software guessed on what those corners are. But the takeaway point here is you can look at the corrected Z range here. So if 0 is in the center, you can see we're varying from 0 to 0.4, and then finally as you move pretty close to the edges about 0.8 or 1.2. So this contour map shows you that you've got a nice, decent surface in here to continue the analysis. So that's about a 6 by 6 millimeter area. Then if you image it, use the white LED, you can see the very fine scratches on the outer 30 micron thick area, and then the window looks nice and black and clean because we've done colloidal polish in here. Then that's the NIR LED, so you're seeing the circuitry outside of the window as well as inside the window. And then if we have any water on here, you'll notice the water beads up, it de-wets because it is a nice polished surface. This is a visible illumination with the part removed from the machine and just put under a standard stereo zoom microscope. You can see the nice red glow with the 3 micron thick part. A few other things to talk about. Stacked die, small parts on board. So with a stacked die here, the way this is handled is you thin down or etch down to the top die, and then you take a profile of the part by mechanical. So there's a mechanical profilometer on the machine. It generates this top profile. Then you thin and remove that die using that profile, and then you can adjust the profile as you go through die to die to die. This is an example of small devices such as QFPs and SOT23s on a small board. So this one has been thinned. You can see the shadow of a capacitor right here. This capacitor is annoyingly close to the edge of the die. So this one required an X-ray overlay in order to make sure that I properly targeted this die. Then this is another part on the same board. In this case, I needed to do a top side, so I thinned down to the tops of the wire loops. And then I put a putty material on here, and I used fuming red nitric acid to continue exposure until the die was exposed. To make sure that I didn't get into trouble with it getting around this putty, I used a red potting epoxy around these parts here. Doesn't look nice, but it worked fine. And then that way all the leads were protected from the process. And then this is a few kind of off the beaten path things you can do. So in this case, you have a homebrew arrangement where you've got a board that you can actually attach with some probes and probe some pins on a part while you're coming down with a milling tip and milling and picking up access on a board. So we've got a lead dropped here. We're using the milling tip as the other side of the probe. And then you can measure continuity of traces or cut traces to verify that they're open. You can put, I've already shown where you can put motherboards on here to be able to thin as well. So we're almost done. This case history is with silver dendrites. This was a part that whenever you opened it, the leakage would go away. So I used the machine where I very gently approach this capacitor from the side where the arrow is. And then I had the leads hooked up to a curve tracer so I could watch the parametric instabilities as I was thinning. Once I got extraordinarily close and there was just a little bit of this plastic left along the edge, which you can see right here, then we went into the SEM and looked at these areas where there were open pockets and found silver dendrites. So for more reading, as far as ultra-thin chips are concerned, or to learn more about the pitfalls and benefits of flexible electronics, this is a good reference source. And then in the Failure Analysis Microelectronics Desk reference, these are the two papers which I have in there. And there are a number of other good papers in there as well, dealing with solid immersion lenses and front side prep and front side analysis, delayering, etc. So there are quite a few good resources there. So these are the things we've covered going through this, and I just want to thank you for your attention and have a nice day.